Yeah, thank you very much. And thanks also to the organizers for putting up this very nice conference, which brings forward science and also makes our brains free. So today I'm talking about applying strain to correlated electron systems. And by the end of the talk, I hope that you understand why I call it stress reduces frustration. So I work in Vienna in the city center, so we have a nice institute here nearby Karlsplatz, and my main work is on studying the spin properties of correlated electron systems by nuclear magnetic resonance, and also the charge properties by optical spectroscopy, well, and transport, of course. And this work was performed with collaboration with Kawasugi and Tajima from Japan, also with Cliff Hicks, Andy McKenzie, and Stuart Brown on the strontium ruthenate under strain. And the last part of the talk, the samples on Herbert smithite were provided by Pascal Pufal and Cornelius Grellner. So my work generally spans over the entire electromagnetic spectrum. So we start from transport, we look at nuclear spins, electron spins, phonons, and transitions between interband transitions or just across a gap of a Mott insulator, for instance. And today, I will focus on transport results under strain and also nuclear magnetic resonance under strain, so at DC and at megahertz frequencies. So the topic that we are all discussing here is how can we tailor quantum materials so that we can get properties on demand, essentially. So we have seen that getting light pulses in these materials can change a lot and is very effective. But here I will focus on another technique, so let's say the more fundamental one, just bandwidth tuning by changing the distance between atoms. So if you have atoms far away from each other, the overlap of wave functions is small, so the electrons do not want to hop from one side to the other. If you put the atoms closer to each other, the transfer integral is bigger, and then electrons more tend to go into a metallic phase. And by changing the distance between atoms, you can go from an ordered phase to a metallic phase. Across, you always see superconductivity, or most often. And how we do this, we typically grow different samples by chemical tuning. So we can grow a sample here, another one here, here, by using atoms of different size. Like we did here for different Mott insulators, which one is more correlated than another one, and so we cover different parts in the phase diagram. Then we can start from these positions that we have and apply pressure. So with pressure we go from left to right, so we make the lattice smaller, therefore we make the overlap bigger and electrons tend to move more. However, pressure can only go from left to right, it cannot go to the negative side. This is one of the downturns. And for that, I've been focusing the last years on uniaxial strain, because you can compress a sample from two sides, but you can also pull on the sample, apply tensile strain. Yes?
But there were some substitutions that may create...
Yeah, chemical tuning. I mean, this is... chemical tuning, of course, can bring you either here, or it can place you here. But when you have this sample and you want to modify this sample, by hydrostatic pressure, you can only go to the right. Yeah, but with a strain, you can also pull on the sample, then you have the atoms further apart, and you can also go more to the left. And this is quite useful. And moreover, the uniaxial strain cells that we have nowadays, they allow to tune the correlations sitting at low temperatures. So you can do this at millikelvins, which is also quite useful in our field. So strain itself, it is anisotropic. So if you compress a sample, it will expand in the perpendicular direction and vice versa for tensile strain due to the finite Poisson ratio. And apart from bandwidth tuning, we can also therefore tune the dimensionality. We can take a two-dimensional system and we can make it more one-dimensional by anisotropically compressing it. And moreover, as we will see later in the talk, we can also tune from a square lattice with well-defined antiferromagnetic order to a more frustrated, like triangular lattice, where the magnetic order is not that well-defined. And uniaxial strain is the right tuning knob to tune between these phases. And today I will give an overview of how to tune superconductivity, the Mott transition in a frustrated material, and also to directly tune frustration in a magnetically ordered system, so that you can, I hope to persuade you that this technique is quite useful. So we start with strontium ruthenate under strain, where we observed an unexpected behavior. So this material is isostructural to the cuprates. So it has the same lattice structure like lanthanum barium cuprate. But strontium ruthenate itself is a metal without doping, and it is an unconventional superconductor, which has been observed early on. And quite interestingly, when you compress it uniaxially, the TC goes from 1.5 Kelvin up to 3.5 Kelvin, so a boost of 250%. Consider you have YBCO with 100 Kelvin TC, you do 250%. Yeah, it doesn't work yet, but yeah, it's a quite a substantial effect, and it was achieved because of the advent of piezoelectric strain cells, which can, at low temperatures, contract or expand, which were developed by Cliff Hicks and Andy McKenzie. And they were developed in order to study the unconventional superconductivity of this material, which was predicted to be an electronic analog of helium-3. So helium-3, as we know, has a superfluid phase, which has a chiral triplet order parameter. So very unconventional, because most superconductors that we know are singlet superconductors. And it appeared that early experimental evidence by nuclear magnetic resonance seemed to provide evidence for such a triplet state. And apart from that, there was an interesting observation that nearby the superconducting transition, there was time reversal symmetry breaking, seen by MUSR and also by Kerr effect by Kapitulnik's group. And well, let me quickly remind you what is the difference between singlet and triplet superconductors. A singlet superconductor has antiparallel spins, so the Cooper pair has 0 magnetization. In a triplet, we have parallel spins, so the magnetization is the same like in the metallic state. But how to measure that? We cannot just put it in a magnetometer, like in a squid, because in a superconducting state, we measure diamagnetism. And this diamagnetism is much bigger than Pauli paramagnetism, so we need a different probe. And the probe that we use for that is nuclear magnetic resonance. So in nuclear magnetic resonance, if we have a nucleus with a spin and apply a magnetic field, then we have a spin up state which lowers in energy, spin down state increasing in energy, and we can drive transition from up to down state with the Zeeman energy. So in the end, we have this gyromagnetic ratio gamma. So this term here defined by essentially charge divided by mass of the particle gives us the resonance frequency. And in an NMR experiment, we then see like the NMR absorption at the resonance frequency F0, which is just gamma times this external magnetic field, if the nucleus is in vacuum. If we now have the nucleus in a solid with conduction electrons around it, then the conduction electrons themselves, they are magnetized by this magnetic field, so they contribute an additional magnetic field. And therefore, the NMR line is shifted. And the shift, delta F, is proportional to the susceptibility of the conduction electrons, so this is known as the night shift. So we can extract the susceptibility of the conduction electrons from the NMR spectrum. Apart from that, also if we have magnetic order, we will see a splitting of the lines for antiferromagnets. So the spin up will have higher frequency than the spin down, and so this is a pretty useful tool to study magnetism and superconductivity. So these experiments have been performed on strontium ruthenate like more than 20 years ago by Ishida and Maeno. And it was seen that there is no change of the night shift, so they have different oxygen sites here. But as crossing the TC, which is 1.2 Kelvin here, they saw no change. So they concluded magnetization is like normal state, so it must be a triplet. This was for 20 years the story that was predominant. But then I did a postdoc in Los Angeles, and we studied the high strain state of strontium ruthenate, where we have a higher TC and a higher critical field, so at this peak of the TC. And surprisingly, we found that there is a change of night shift as we cross the superconducting transition. So these two results are kind of strikingly different. And the question is now, is there a change of superconductivity when going from 0 strain to high strain, or what is happening? To make the story short, this measurement was wrong. So here they thought the sample is superconducting, but the sample itself heated up. So these data points are just the same metallic response like at higher temperature. So this was an experimental artifact. And later on, the results that we had here were also confirmed by the Ishida and Maeno themselves and also by other people. So let me quickly illustrate how this heating effect occurred. So if you have an NMR pulse, over the next millisecond or so, you will acquire the NMR spectrum. So this is the time domain measurement that we do. We just acquire the radio frequency signal and make a Fourier transform, and this gives us the NMR spectrum that we see here. And in the case of this material, the sample heated up from like millikelvins to above 1 Kelvin, and then it was in the normal state while this NMR spectrum was acquired. So this is why in the end the old measurement was showing that there is no change of night shift, simply because it just measured for a short time the normal state. And then the sample cools down again. We now did the measurement under conditions that we have a higher TC because we applied strain. So we were never in the situation that the heating would heat it up to the normal state because TC is higher. And therefore, sitting at this position just provided us the necessary insight in order to know what is the real superconductivity of this material. Then we looked at zero strain. So this is without any strain applied, and we just used NMR pulses with lower energy. So with high energy, we also saw the heating effect, but with low energy, we saw the real spectrum of the superconductor, which indeed shifted away from this position. Well, and then we quantified even how much magnetization do the Cooper pairs have. So we have to remind that the susceptibility combines quasi-particles, which are induced by the magnetic field, because it's a nodal superconductor, and the condensate contribution. And we can account for the quasi-particle contribution by looking at the Sommerfeld coefficient of specific heat. And by just subtracting the two, what we get is only the response of the superconductor, and we see there's no magnetization left, so it is a singlet superconductor. So this is clear now. There are, of course, discussions on what type of superconductor, whether it is a two-component order parameter or not. Well, this goes on, and we certainly answered with this experiment that strontium luthenate is not an analog of helium-3. But can we consider another material that is an analog of helium-3? Yes, we can. And we will see a frustrated Mott insulator is indeed a realization of helium-3, but with charge. So for that, let's quickly remind of phase diagrams of typical liquids and solids. If we have, like for water, we have a solid at low temperature, then we increase temperature, we melt it into a liquid. This is what we understand in our classical world. If we now have a quantum fluid like helium-3, there is a range where you have a solid and you cool it down and then it melts. So exactly the opposite. It's known as the Pomeranchuk effect. There was a Nobel Prize on this. And the explanation is also known. So the entropy of localized spins in the solid phase is higher than the entropy in the liquid phase. And therefore, we have this positive slope of the phase boundary due to Clausius-Clapeyron equation. And the reason is helium-3 is a fermion. It has a spin 1/2 nuclear spin. Well, and electrons are also fermions. They have a spin 1/2. And as we see the phase diagram of a Mott insulator as a function of temperature and pressure, we see that the Mott insulator with localized charges is at higher temperature than the metal where the charges are moving. So it's exactly the same effect. And in both cases, we do see that between the metal and the insulator, there is a superfluid phase. So in the Mott insulator, it's just a superconductor because it's charged. And in helium-3, it's neutral, so it's just a superfluid. And the behavior is probably the same like in neutron stars somewhere else, where the neutrons condense and form such a coherent state. Good. We have heard about the Mott transition, which is driven by Coulomb repulsion and wave function overlap. So particles want to be far away from each other because they repel each other, somewhat like humans. And if we now apply, so if we put the atoms which are far away, then we have an insulator. And if we push them closer together, then they become a metal. And this way we can apply pressure or strain and tune the Mott transition. And importantly, at low temperatures, the Mott insulator has itinerant exchange interactions, which cause this exchange interaction J proportional to T square over U. So we have an antiferromagnet at low temperature, which we saw in the last talk also. And this is seen in cuprates, this is seen in vanadium oxides, and also in organic conductors, which I will focus on in the next slides. But in all these materials, we have approximately a square lattice. So we have spin down, spin up, spin down, into left, right, and up, down. But what happens if we put the spins on a triangle? Then we can align these two spins. They are happy, but this one doesn't know whether to point up or down. So we have frustration. And yeah, if we have too many choices, we cannot really decide. And as a result, magnetic order is suppressed, and we can get quantum spin liquid behavior. So yeah, here you see illustrated that all the arrangements, one of the bonds is not antiferromagnetically aligned. And these type of effects are seen in honeycomb triangular or Kagome lattices. Well, how do the electrons arrange instead? So they typically form valence bonds, and the valence bonds are just spin singlets. Either they form ordered valence bonds, like in a valence bond solid, or in 1D it's called a spin pile state. Or they can form resonating disordered valence bonds, as suggested by Phil Anderson, possibly even quantum entangled. And the natural excitations in such a system are neutral spin 1/2s, which is a spin-on. And the idea is that these chargeless spin particles can transmit quantum information, and this is what we write in the abstracts when we write the paper. So, but we have to find materials which do show this type of behavior. So we look at these organic systems, which are quasi-two-dimensional layered systems. So the electrons predominantly interact along the horizontal direction. And within the layers, we have a triangular lattice. On each of these circles, we have one spin 1/2 sitting. So this is a nice realization of a triangular lattice. And when comparing to a material which is more square-like, here we have antiferromagnetism, here we have a splitting of the NMR lines. The triangular lattice material does not show any splitting. So there is no antiferromagnetism, frustration suppresses it. And the question was in the beginning, like 20 years ago, after measurements by Kanoda sensei, whether this is a gapless spin liquid. And a few years ago, we did ESR measurement, and we found it has a spin gap. So there is a strong reduction of spin susceptibility around 6 Kelvin. And it kind of rules out a gapless spin liquid state, but there are many other options what gapped spin state it can be. So for that, we have to study it in more detail. And here we now looked at it by tuning it through the phase diagram. So how did we did it? We took a very thin sample of this material, put it on a piece of plastics on PET. Then by cooling, the PET compressed because it has a strong contraction. This means that the sample, which is originally insulating, was pushed to the metallic state, so along this red arrow. So at low temperatures, it shows metallic properties. And then we could bend the substrate so that the sample is extended again. This way, we pushed it back from the metallic to the insulating state, and we had a very high resolution of the metal-insulator transition. So here you see the result. So in the beginning, when we have no tensile strain, we just have this maximum of resistivity with metallic behavior below and insulating above, and we also see superconductivity. When we then apply this tensile strain, the maximum goes to lower temperatures, and eventually we only see insulating behavior. So then we are just, we go from here to here, and then we have only in red this insulating behavior. But what we found in addition was that there was a small minimum, so a re-entrance of the insulating behavior. And this indicates that there is a second phase occurring. And this phase that we have here, it must have a smaller spin entropy than the paramagnetic mod insulator. And this would be quite consistent with the valence bond solid scenario. So here's a phase diagram of a valence bond solid. And the phase diagrams look identical, experimental data look identical. So in principle, this seems to be the most viable option. I still have 2 minutes, so 19. Good, but let me quickly flush through the last point. So we use uniaxial strain to directly tune the frustration in the material. So for that, we look at Herbert-Smithite-like systems, and we take a compound which has a T-neal, so a magnetic transition at 2.2 Kelvin. And now the question is, how can we reduce the frustration? And the obvious thing is, if we move one of the particles further away, then it's easier to decide for the system. This we do like from a Kagome lattice, which is isotropic with same J in all directions. When we compress it along one direction, J is bigger than along the others, so magnetism can form more easily. And it was suggested by Heisenberg model on a distorted Kagome lattice that the magnetic transition increases linearly with frustration reduction. Good, then we put the sample on a strain cell, so we glue it with this black stuff here. Here you see the alignment of the Kagome lattice. Then we put a coil around the sample. It's not the nicest coil, but it allowed us to measure the spin lattice relaxation rate. In black, you see the zero strain result, and when we apply strain, the temperature increases. Exactly the behavior that we expected. So, and we see in the inset, the change of transition temperature as a function of strain is linear, exactly like the model predicted. So, I mean, the effect is not that spectacular. It's only 10% of change, but I believe if we look at other materials which are between magnetism, valence bond solid, and possibly spin liquid, we can obtain much bigger, more interesting effects. So this was kind of a proof of principle result. Well, then, thank you for listening. I hope you saw some nice insights what we can do with strain.